Hello everyone, today we will be finishing up our discussion of networks and trees with what is known as Kruskal's algorithm. Now, Kruskal's algorithm is basically just a method for calculating the minimum or maximum spanning tree of a network. Now, as you may remember from the last video, a spanning tree for a network is basically just a tree or network with no circuits that spans every vertex of the full network. And when we have a weighted network, such as this one shown over here on the left, the minimum spanning tree is going to be whichever spanning tree exists for that network that has the lowest total weight. And the maximum spanning tree is basically the opposite of that, whichever spanning tree has the highest total weight. Now, Kruskal's algorithm essentially revolves around the idea of adding weight or adding edges in order of increasing or decreasing weight depending on if we're going for the minimum or maximum spanning tree. And one thing that's nice about it, it's fairly straightforward, and it always is going to give us an optimal solution for either the minimum or maximum spanning tree, whichever one we're going for. Now, looking at our weighted network over here, we have 12 vertices, which means that our spanning tree, either minimum or maximum spanning tree, is going to have 11 edges, or in other words, n minus 1 edges. So let's start with the minimum spanning tree. Now, the minimum spanning tree, we are going to start with whatever edge on this graph has the lowest weight. So that would be this edge right here from F to G with a weight of 3. So we're going to add that to our tree. Then we're going to go to the next lowest weight, which is 4 right here from I to J. So we're going to add that. And basically, we're going to keep doing this, basically just adding the next lowest and then the next lowest and the next lowest until we have our 11 edges to span the full network. But one thing that we have to be careful of is that we do not want to create any circuits, because the instant that you create a circuit, we no longer have a tree. By definition, a tree has to have no circuits in it. So the next lowest weight that we see anywhere on here is 5, going from F to I and also from A to B. Both of those we can go ahead and add. No circuits created there. The next lowest we see is 6, going from F to H, so we're going to add that. And then the next lowest is 7, and we have 3 edges with a weight of 7, but we can only add 2 of them. So this one from D to E, we can add no problem. Same thing with this one going from J to K, no problem there. But this third one right here going from I to H, if we were to add that, we would be creating a closed circuit right here between F, I, and H. We don't want to do this because, once again, if we create a circuit, that means we no longer have a tree. So we're not going to include that edge in our graph, or in our minimum spanning tree, rather. Next lowest on here is 8, going from E to F. And then next lowest, we have 9 going from B to E. We also have a 9 going from I to K over here, but we don't want to add that because that's going to create a circuit. The next lowest that we see, sorry, we missed one, 8 going from B to C. My apologies, we should have added that before we added the 9s, but in any case, we still have no circuits, and so we're good here. Next, we have 10. We have 2 edges that have 10, B to D, which we don't want to add because that's going to create a circuit, and K to L. And at this point, we now have included all of the vertices in this graph. And if we count up the edges, we find that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges, just like we said that we were supposed to have for a tree. So now, if we want to find the total weight of our minimum spanning tree, basically all we're going to do is take the weights of all of these different edges that we've included and add them all up. So from A to B, we have 5, and then 8 and 9, 7 and 8, 6 and 3, 5 and 4, and then 7 and 10. So if we add all of these up, we get a total of 72. So 72 is the total weight for our minimum spanning tree. Now, when we want to find the maximum spanning tree, we're going to use Kruskal's algorithm again, but we're going to do things a little bit differently. Now, there's a couple different ways that you can accomplish finding the maximum spanning tree using Kruskal's algorithm. One of them would be to just invert the signs. So basically change all of these to negatives and then find the minimum spanning tree. The other way that I think is simpler and accomplishes the exact same thing is basically to just add the edges, but go in with the positive numbers on here, and just go in the reverse order of what we did for the minimum spanning tree. This is doing the exact same thing, but in my opinion, it's a little bit of an easier way to think about it. So what we're going to do, if we look at this graph, we're going to find the edge with the highest weight instead of starting with the lowest weight. So that would be C to E with a weight of 11. So we're going to add that edge to our tree. Next highest is 10, which we have two places, from C to D and from K to L. Next highest is 9. We also have that in two places, B to E and I to K. Next, 8 from E to F. We also have one here from B to C, but we don't want to add that because that's going to make a circuit. But we can go ahead and add the E to F one. Next is 7, which we have three different places. So from H to I, from J to K, and from D to E, but we don't want to add the D to E one because that also creates a circuit. Next, we have 6 from H to F. Next, we have 5 from A to B. And then 4, we also have 5 from F to I, but that would create a circuit. 4 from I to J also would create a circuit, so that leaves us with 3 from F to G. So at this point, we've got all of our vertices included, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 edges, just like we said we were going to. So now we're going to do the same thing that we did for the minimum spanning tree. We're going to add up the weights of all of these to find the total weight of the tree. So we have 5 here. We have 9 from B to E. 11 and 10. 8, 3, and 6. 7 and 9. And then 7 and 10 finally. So if we add all of these weights up, that's going to give us a total of 85. So 85 is going to be the total weight for our maximum spanning tree. Again, Kruskal's algorithm is nice because it's fairly straightforward and it's always going to give us an optimal solution. Thank you for watching, and as always, I'm happy to help with questions.